Find the runoff in cubic feet per second from area C. In this problem, runoff from 7 areas combine to create a stream flow which has a total flow rate of 109 cubic feet per second. Quantities of potassium, chloride, nitrate, calcium, sulfate, magnesium, bicarbonate, and sodium are measured for the total stream flow, and the concentration of each ion per unit flow rate is known for each area. If we define x1 through x7 as the runoff in cubic feet per second from area A through area G, then our water balance constraint will be the sum of the 7 x values equals 109 cubic feet per second, where all 7 x values must be non-negative. In addition to this water mass balance constraint, there are also 8 ion mass balance constraints, where Cij represents the quantity of ion J from runoff area I, and we'll define its units as ions per cubic feet per second. All values of Cij are known. As mentioned previously, the values of x represent the runoff flow rate and are in units of cubic feet per second. These x values are the decision variables. Bj is the total quantity of ion J found in the combined stream flow at the sampling site at the bottom of the reach. If we assign J equals 1 to bicarbonate, then the C values of 34.2, 158, 366, 159, 281, 48.8, and 360 are the concentrations of bicarbonate ions per cubic foot per second of runoff flow from area A through area G, respectively. The x variables represent the flow rates from the 7 areas, and the value of 9,699 is the quantity of bicarbonate ions measured in the reach downstream of all 7 areas. If we assign J equals 2 to chloride, a similar mass balance constraint is developed, as well as mass balance constraints for nitrate, J equals 3, sulfate, J equals 4, calcium, J equals 5, magnesium, J equals 6, sodium, J equals 7, and potassium, J equals 8. Since there are 9 constraints and only 7 decision variables so far, there may be no feasible solution without introducing an error term, E, as additional decision variables in the left-hand side of each ion mass balance constraint. Since the total calculated bicarbonate ions in the stream may be more or less than 9,699 ions, we'll expand the error term to be EJ plus and EJ minus, where both error terms are non-negative. The error variables are added to the remaining ion balance constraints as well, as shown here for the chloride, nitrate, and sulfate constraints. All error variables, EJ plus and EJ minus, shall be non-negative. Once the network tableau is set up, we'll assign positive phase 2 cost coefficients to all error terms EJ plus and EJ minus, so that the simplex algorithm will seek to minimize the sum of the error terms. Since there is no error term in the water mass balance constraint, the sum of the runoff flow rates from all 7 areas will equal exactly 109 cubic feet per second. Since there is an equality constraint, we'll add an artificial variable, v1, which is initially 109, and will help us find an initial feasible solution. The decision variables in this problem include the runoff flow rates x1 through x7 with initial values of 0. The positive air variables E1 plus through E8 plus with initial values of 0. The negative air values E1 minus through E8 minus with initial values of Bj, where Bj equals the right-hand side of the ion balance constraints, and the artificial variable V1 with initial value of 109, which is equal to the right-hand side of the water balance constraint. The units of all these variables are in cubic feet per second, and all are non-negative. Now we're ready to set up the network tableau. Due to space, the values in the tableau are rounded and not exact. Variable V1 and variables E1 minus through E8 minus are in the initial basis, with initial values shown in column B. The phase 1 cost coefficients are listed in row Z1 and equal to 0 for all variables except the variable V1, where the phase 1 cost coefficient for variable V1 equals 1. The phase 2 cost coefficients equal 0 for variables x1 through x7, 0 for artificial variable V1, and 1 for all air variables EJ plus and EJ minus. The water balance constraint coefficients are shown on row V1, and the unit concentration values for the ion balance constraints are shown on rows E1 minus through E8 minus. First we'll solve the phase 1 to find an initial feasible basis, which does not include artificial variable V1. Putting the tableau in canonical form will require we pivot around variable V1, which involves subtracting 1 times row V1 from row Z1. Now the initial phase 1 cost coefficients are all -1 for decision variables x1 through x7. If we choose variable x1 to enter the basis, it would take the place of variable V1 when performing the ratio test. Pivoting about variable x1 would involve adding 1 times row x1 to row z1, subtracting 34.2 times row x1 from row e1 minus, subtracting 0.89 times row x1 from row E2 minus, subtracting 2.09 times row x1 from row E3 minus, subtracting 15.1 times row x1 from row E4 minus, subtracting 2.75 times row x1 from row E5 minus, as well as subtracting 1.25 times row x1 from row E6 minus, subtracting 3.5 times row x1 from row E7 minus, and subtracting 2.2 times row x1 from row E8 minus. At this point, phase 1 is complete, since all phase 1 cost coefficients equal 0, except for the artificial variable, whose cost coefficient equals 1. Row Z1 and column V1 are removed from the tableau, and we begin with phase 2. We first must put the tableau into canonical form by pivoting about variables E1 minus, E2 minus, E3 minus, all the way through E8 minus, which involves subtracting 1 times row E1 minus from row Z2, subtracting 1 times row E2 minus from row Z2, and so on, all the way down until subtracting 1 times row E8 minus from row Z2. After the pivot operation, the reduced cost coefficient for variable x7, which represents the runoff flow rate from area G, is the most negative and will enter the tableau. From the ratio test, 2,310 divided by 875.5 is a smaller positive quotient than all other rows. Therefore, variable x7 will enter the basis for variable E7 minus. Pivoting about variable x7 involves dividing row x7 by 875.5, then adding 5,929 times row x7 to row z2, subtracting 106.4 times row x7 from row x1, subtracting 5,095 times row x7 from row E1 minus, subtracting 94.31 times row x7 from row E2 minus, subtracting 34.01 times row x7 from row E3 minus, subtracting 3,935 times row x7 from row E4 minus, subtracting 253.3 times row x7 from row E5 minus, subtracting 397.8 times row x7 from row E6 minus, and subtracting 7.3 times row x7 from row E8 minus. At this point, variable x3, which represents runoff flow rate from area C, has the lowest reduced cost coefficient and will next enter the basis in place of variable E4 minus. After pivoting about variable x3, the tableau is again in canonical form. Next, variable x5, which represents the runoff flow rate from area E, enters the tableau for variable E6 minus. After pivoting about variable x5, the tableau is again in canonical form. Next, variable x2, which represents the runoff from area B, will enter the basis in place of variable E1 minus. After pivoting about variable x2, the tableau is in canonical form, and we're again ready to price out. This time, variable x4 will replace variable E2 minus in the basis. After pivoting about variable x4, the tableau is updated. Next, variable x6, which represents the runoff flow rate from area F, enters the basis in place of variable E5 minus. After pivoting about variable x6, the tableau is in canonical form. At this point, the only remaining variable with a negative reduced cost coefficient is variable E6 plus. Variable E6 plus will replace variable E3 minus in the basis, since 155.6 divided by 10.83 has the smallest positive ratio of BI over AIT for row I in column T. After pivoting about variable E6 plus, the tableau is in canonical form. All reduced cost coefficients of non-basic variables are negative. This ensures we have found an optimal L1 norm estimation of runoff flow rates for the 7 areas. These runoff values include an overestimation of 14.37 ions of the sixth ion, magnesium, and an underestimation of 0.92 ions of the seventh ion, sodium. If the estimated runoff flow rates from each of the individual areas, which sum to 109 cubic feet per second, are shown on the diagram, we can identify the flow rate from area C, which is 5.17 cubic feet per second. When reviewing the possible solutions, the answer is A.